Welcome back to week 12, chapter 6, part 2. Okay, so this week we're going to be looking at calorimetry, Hess's law, and standard enthalpies of formation. So calorimetry, our first one here, is all about measuring heat. Okay, calorimetry is one way that you would figure out, say, how many calories are in a food. Okay, and then the next thing that we have is Hess's law, and this is using different parts of equations in order to find an overall equation in terms of heat gained or lost. And then last, we'll have standard enthalpies of formation, which I'm leaving in pink also, because it's sort of related to Hess's law, except for the fact that you're working it with a different set of numbers. All right, so let's go ahead and begin. First of all, calorimetry. Okay, so when we're doing calorimetry, you're going to be working with the equation that Q, remember Q means heat, okay? That Q is equal to SM delta T. Now, I've seen online technically, you can use a C for S instead. C actually means molar heat capacity, but sometimes, and I'll say some online videos write this. They'll write, I see this a lot, MC delta T, because it's MCAT. Okay. So if you see this, it's probably the same thing. So what these things stand for is our S is specific heat. And that is the amount of heat needed to raise 1 degree of water by 1 degree Celsius. You don't really need to know that too much, except for the fact that the units for specific heat are in joules per gram degree Celsius. Okay, so because of that, we need to make sure that this M, or mass, has to be in grams so that it agrees with our constant. And then we will have delta T. Okay, now in chapter 5, all of our change in temperature was always in kelvins. And there was a reason for that. However, this delta T does not need to be in kelvins because we're looking at the change, and a Kelvin and a degree Celsius is exactly the same increment. So this can be our temperature. So you would say your final temperature in degrees Celsius minus your initial temperature in degrees Celsius, or T2 minus T1, if you prefer. Okay, so the specific heat, I used a word here. Specific heat is a constant, but it's not a constant like R was a constant. It's because it's different for every single thing. Okay, so a specific heat is a constant for each material, let's say. Okay, so for example, the specific heat for water is 4.18 joules per gram degree Celsius. Okay, let me see if I can find in my notes something else that I might have. All right, the specific heat for iron is 0.45 joules per gram degree Celsius. And it's different for every substance that you're going to work with. Okay, so what you're going to need is, that's going to be a piece of information that you will be given in a problem. If we were working this in class and we were sitting right there with our textbooks, I would not give you everything because you would just look it up in your textbook. But I know that not all of you have an actual hard copy textbook when we're doing this online. So, okay, let's take a look at some problems for calorimetry. Okay, let's look at a really simple one. Let's say that we have, okay, actually here, let me, how much heat energy is required, and I'm doing this a little differently than what's in the slides, just so that it's a little different. How much heat energy is required to raise 37.5 grams of water from 9.32 degrees Celsius to 17.98 degrees Celsius. Okay, all right. So here what we have is we have the mass of our water. And here we actually have our delta T. And it's final minus initial, not always positive minus negative, okay? So it's okay to end up with a negative number here, but we won't this time because we're increasing. So if we do 17.98 minus 9.32, we get a delta T of 8.66 degrees Celsius, okay? And if you remember on the previous slide, I mentioned that the specific heat of water is 4.18 joules per gram degree Celsius. So let's see how much heat energy is required to raise our water by this much in temperature. Okay, so we'll say Q, because that's heat energy, is equal to SM delta T. So our specific heat, 4.18, times my mass, 37.5, times my delta T, 8.66. And just to review, that's S, M, and delta T. Okay, so we have 4.18 times 37.5 times 8.66. And my calculator gives me this number, 1,357.455. And our grams cancel and our degrees cancel, so the units for this will be in joules. However, I look at this and 1, 2, 3, 1, 2, 3, I can only have 3 significant figures. Okay, so with significant figures, this becomes 1,360 joules. And so that means that I will require 1,360 joules, of heat energy be added to my system in order to raise my temperature by this much. Okay, let's take a look at a couple of other possibilities. Let's now look at, okay, so everybody remember this. I'm actually going to take a couple of little notes so that I can remember what I'm working on here. Okay, and what we're going to do, hang on. Actually, I'm going to start a whole new problem. Don't worry. Okay, so now let's take a look at what happens when we're mixing two different things. Because remember that the heat lost by the system equals the heat gained by the surroundings. okay? And the opposite is also true, that the heat gain by the system equals the heat lost by the surroundings. So the way that we could say that mathematically is that Q of the system equals negative Q of the surroundings. And if we're mixing two things together, we can use this to determine all kinds of things. One thing that we can use this to determine is that we can use this to determine okay, I was hoping that I had something here in front of me, but I don't. I have something else, so sorry. Okay, so we can use this to determine a whole bunch of things. And an example of that could be this. Let's say that I have a beaker of water, okay, and this is water. And in this beaker of water, I have 500 grams of water, and we already said that's 4.18 joules per gram degree Celsius. Okay, so there's a mass, and I have my water. I'm going to make it very, very chilly water so that I have room to go with this. Let's make this water 5.0 degrees Celsius. Okay, now I want to add to it a piece of iron. So let's say that I have my iron here, and I'm going to add my iron to my water. Okay, so now my iron has a specific heat of 0.45 joules per gram degree Celsius. Okay, and my iron has, this is about 250 grams, and its temperature is at 98.0 degrees Celsius. And I want to know, what is the final temperature? Well, I can use this setup for that. So for example, Q of my system is going to be the specific heat of my system, okay? But in this case, we're not going to use system and surroundings, because what we're going to basically be looking at is that our two things here are water and iron. So the specific heat of my iron times the mass of my iron times the delta T, or the change in temperature of my iron, is equal to the opposite of the specific heat of my water times the mass of my water times the change in temperature of my water. Okay, now I have the specific heat of both items. I have the mass of both items. I have the initial temperature for both items, but I don't have the final temperature of the water, and I don't have the final temperature of the iron. So what I need to do is I need to recognize that they will have the same final temperature, because they're going to be allowed to equilibrate. So I'm going to do the math like this. 0.45 is my specific heat of iron. 250 grams is the mass of my iron. And actually, I'm going to run out of room. There. The change in temperature of my iron is T final minus 98. Now, don't forget that negative sign. That's very important. Specific heat of my water is 4.18. The mass of my water is 500. And the change in temperature of my water is T final minus 5 degrees. And now what I'm going to do is I'm going to solve this. Okay, here's my variable. And this is where we're really going to use our algebra a lot. So I say 0.45 times 250 times TF. So I'm doing a distribution here. Okay, so 0.45 times 250 is 112.5 TF. I'm not going to worry about my significant figures just yet. Minus, okay, now I do 0.45 times 250 times 98. And what I get now is 11,025. And now I work the math on this side. So I have negative 4.18 times 500. And that gives me negative 2,090 TF. And then I have negative 4.18 times 500 times negative 5. So that becomes a positive. And we have 10,450. These numbers are really big, and that's normal for this kind of a problem. So the next thing that we need to do is we need to isolate our variables. Well, I have this negative 2090 TF on this side, so I'm just going to add. I'm going to make everything as positive as possible. Okay. And now I have minus 11,025. And so I'm going to add 11,025 to both sides. And so on the left, I have 112.5 plus 2,090. And I have 2,202.5 TF is equal to, okay, on this side I have 10,450 plus 11,025. And so that equals 21,475. Now I isolate TF by now dividing 21,475 by 2,202.5. It's easier to do the math than it is to say it. And I get a TF value of 9.75 degrees Celsius. Okay. And that really makes sense. You can see that if we compare this, you think, wow, that is so close to this temperature for the water when the iron was so much hotter, except for the fact that in this case, we had twice as much mass for our water, and we had almost 10 times as much for our specific heat. So what that means is that for every gram of iron, it's only donating 0.45 joules of heat, whereas the water requires 4.18 joules of heat for that same temperature increment. Okay, so this is a very normal problem looking at calorimetry. All right, excellent. So let's go on now to Hess's law. Okay, for Hess's law, what we're doing is we're taking a series of equations and we're adding them together to get a final equation. So let's look at a really simple Hess's law problem. First of all, we have an overall reaction that is nitrogen gas plus oxygen gas yields 2 moles of nitrogen dioxide gas. And if we do this in one step, our delta H value for the reaction is 68 kilojoules. Okay, now, not everything in chemistry happens in one step. So let's take a look at this in more than one step. Let's take a look at it in 2 steps. Okay, so those 2 steps would be nitrogen plus oxygen yields 2 moles of nitrogen monoxide. I apologize. I needed that 2 up there. They have to be balanced. And it's a gas, okay? And the delta H value for this, and I'm going to call this equation A, is a positive 180 kilojoules. Now you'll notice that I'm making a big deal about these are all gases. And that is because if these were not gases, if they were liquids for some reason instead of gases, then the delta H value would be different. The delta H value is dependent upon the states within the equation. And that is a very important thing to pay attention to. Okay, so equation B has us getting rid of the nitrogen monoxide as an intermediate. So 2 moles of nitrogen monoxide plus oxygen gas yields 2 moles of nitrogen dioxide. And the delta H value for this one is a negative 112 kilojoules. Okay, now how do we compare these? Well, first of all, what we're going to do is we're going to look at our reactants versus our products. Okay, so here you'll notice that I have 1 mole of N2 and it's right here. Good. All right, and now I have 2 moles of oxygen, and here I have 2 moles of oxygen. And then here I have 2 moles of nitrogen dioxide, and here I have 2 moles of nitrogen dioxide. And you will notice then that you have that what you're doing in the first equation is you're making this intermediate nitrogen monoxide, and then you're consuming it in the second one. So creating, destroying, which means that we can cross out because it's on the product and the reactant side of the equations. Okay, because everything is accountable for here, I can add my delta H values together. And if I take 180 plus negative 112, then I will get 68 kilojoules. And you'll notice that they match. And this is because enthalpy is a state function. So it doesn't matter if we do the whole process in one step or if it takes 2 steps to accomplish it. Okay, so now let's take a look at a slightly more challenging Hess's law problem. Okay. I'll let you know right now, if you go to your recitation, you think, wow, this is really tricky. I will be doing with you guys a really nice, challenging Hess's law problem in recitation. So know that I will help you with some harder Hess's law problems. Okay, so here we have, let's consider the reactions. So here's our target reaction. And that is 2 N2 gas plus 6 H2O. And in this case, it's a gas. Remember that state matters. If this were a liquid, then the delta H value at the end would be different. And now we have 3 moles of oxygen gas and 4 moles of ammonia. And that is also a gas. And what we want to know here is our delta H value. All right, so let's take a look at a couple of other problems. We don't have a delta H value for this reaction, but we do have delta H values for a couple of other reactions. Those are as follows. We have NH3 as a gas yielding a half of a mole of N2. And you'll find that in chapter 6, in chapter 3, when we were balancing equations, we didn't use halves very often or fractions. We tried everything to be a whole number. However, in this chapter, that's just fine to have that. Okay, so we have half a mole of nitrogen gas plus 3/2 moles of hydrogen gas. And this process is a positive 46 kilojoules. And it's a positive enthalpy, which means it's endothermic. And now the next process that we have here is, and I'm gonna just change colors here so I can color coordinate as we go along. We have 2 moles of hydrogen gas. Oops. Plus 1 mole of oxygen gas. And that yields 2 moles of water. And now this is also being written as a gas. And again, very important. If we were making water with this instead of a gas, liquid water instead of gaseous water, this delta H value would be different. And this is negative 484 kilojoules. But this reaction is written. Okay, now what we need is we need to figure out how to make these 2 reactions down here look like our target reaction. And the way I like to do that is by finding my target. So here I have nitrogen, and here's my nitrogen. And I need 6 moles of water, and here I have 2 moles of water. And I need 3 moles of oxygen, and here I have 1 mole of oxygen. And then I need 4 moles of ammonia, and here I have 1 mole of ammonia. And then I have some hydrogen that I know I need to get rid of. So let's take a look at our reactions now. First of all, let's take a look at this first one. We need this to be reversed, because see how we have 4 moles of ammonia on the right in our target reaction in our products, but we have 1 mole of ammonia here in our reactants? That means that what we need to do is we need to flip this one over so that it's going backwards, okay? And we need to multiply it by 4. And then we'll have what we have here in the correct locations. But that means that we also need to do that with our delta H, flip and multiply by 4. So now let's take a look at this equation. 4 times a half means 2 moles of N2 plus, now 4 times 3 is 12, divided by 2 is 6. So we'll have 6 moles of hydrogen, yielding 4 moles of ammonia. Okay, and now the new delta H value for that is going to be a negative because flipping it means changing the sign. And I need to multiply 46 by 4. And so I get negative 184 kilojoules for this equation. So the delta H value depends exactly on what we're looking at. Now let's look at the one that we have down here. I need 3 moles of oxygen in my products, but I have 1 mole of oxygen in my reactants. I need 6 moles of water in my reactants, but I have 2 moles of water in my products. So what that means is, first of all, I need to flip this one around also, and I need 3, so I'm going to multiply it by 3. Because I do that, I also need to flip my delta H and multiply it by 3. And again, that means I'm going to change my sign. Okay, so now let's rewrite this one. Now I have 6 moles of gaseous water decomposing to form 6 moles of hydrogen gas and 3 moles of oxygen gas. And that means that my delta H value is now going to be a positive. And I do 484 times 3, or 1,452 kilojoules. Now, one way to check that I have done this correctly is to examine whether or not I can cancel things out. And here I see that I have 6 moles of hydrogen on my reactant and 6 moles of hydrogen on my products in this equation. and I can see that everything matches my target equation, which means that I can take these two delta H values and I can add them together. And what I get is an overall delta H reaction of 1,268 kilojoules. And again, if that's feeling really kind of difficult, there are problems for Hess's law in the annotations, links to videos for that, and we'll be going over it in recitation as well. One last thing this evening, and that is, oh, sorry, it's evening here. And that is what we call standard enthalpies of formation. A standard enthalpy of formation is this. So your book doesn't go into this in a lot of detail, but I think it might be interesting for you guys to see where it comes from. Okay, so the standard enthalpy of formation, let's take a look at water, okay, for water as a liquid, and that's really important there. Okay, so for water as a liquid, so what this means is that if we have, it means that we're making 1 mole of our compound. And when we make 1 mole of our compound at standard state, it's going to have a delta H value associated with it. And for water, that's negative 286 kilojoules per mole. And then how do we make this? Well, it would be with 1 mole of hydrogen gas and a 1/2 mole of oxygen gas. Now, I want to show you something. Remember how I've been kind of talking a lot about how the states are different. Well, if this were hydrogen gas plus oxygen gas forming water vapor, water gas, okay, then what I would actually have here is negative 242 kilojoules per mole. Okay, so that's why it's really important to know what your state is. And this is a standard enthalpy of formation. It's basically the amount of heat energy that is gained or lost when a compound is created. Because of that, anything in its natural state will be 0. So, and okay, so standard enthalpy of formation, this is actually, has some different symbols. So this is our standard enthalpy of formation specifically. Okay, so the standard enthalpy of formation for oxygen gas is 0. And let's say for sodium metal, that would be 0. For argon gas, that would be 0. For liquid bromine, oops, bromine is a liquid at room temp, that would be 0. Okay, so for anything in its natural state, remember, and we've seen this before when we were doing oxidation states, right? That would be 0. So this is kind of the same thing. All right, now let's take a look at how we do the math for something like this. And I'm going to, you can read in the slides for the exact formula for that. But what I want to do is show this to you without the formula, because sometimes the formula confuses people because they don't understand what the capital sigma for sum is. Okay, so based on that, let's take a look at a problem. Let's say that we have 4 moles of ammonia plus 5 moles of oxygen gas, yielding 4 moles of nitrogen dioxide and 6 moles of liquid water, okay? And we want to know, what is the delta H value for this reaction? Well, if you don't have equations for Hess's law, you can look up standard enthalpies of formation. Now, at standard state for ammonia, this is negative 46 kilojoules per mole. This is oxygen gas, so this one's 0. Okay. This is nitrogen dioxide, so this one is a positive 34 kilojoules per mole. And this liquid water is negative 286 kilojoules per mole. Okay, so whenever we're finding our delta H of reaction here, delta H of our reaction is going to be products minus reactants. Okay, all right, so products minus reactants. So the way we do this now is we say, okay, well, let's look at our products. We have 4 moles of our nitrogen dioxide. So this will be 4 times 34 plus the rest of our products. And that'll be 6 times negative 286. Now I'm going to subtract my reactants. So first of all, I have 4 moles of ammonia. So 4 times 46 plus, okay, and I'm going to change color for this. I'm only going to show this because, but here we have, here we have 5 moles of water times 0, okay? So you guys all know in looking at this that this goes away, right? 5 times 0 is just 0, so we can ignore it. So most people don't write the zeros in, okay? So now, we pull out our calculator. Don't forget your signs. So I have 4 times positive 34. And so this one becomes 136. Now here I have plus, and this is a negative. So I'm going to go ahead and put in a negative there. So I have 6 times 286, 1,716. And here I have a minus, and then a negative sign. So this becomes plus 4 times 46. So plus 184. And I combine all these. And I get a final answer for my delta H value of negative 1,396. Whoops. Started my K too early. 1,396 kilojoules. Okay, excellent. I'll see you guys in recitation.